to the cloud. All right. Because I want to catch the bunny photos, I mean the bunny videos.
Yeah.
We can leave that on.
Oh, very good.
Excellent.
So when do you anticipate getting back to campus, Melanie? Is there any word on that?
We've got, those of us who are like lab managers and things like that have to, occasionally go on campus at the moment. So I'm probably there a day a week or half a day a week, something like that. And then, and so that we'll be able to go back progressively more and more as time goes on.
Yeah.
So I think for the moment, nothing's really changing with this change tonight. But in early November, once we hit 80%, I think things can go a bit more back to normal. So so it's good. I mean, I think it's really, the PhD students have really been suffering.
That's been the worst. I mean, we've got a lot of our PhD students, particularly the ones doing lab work, are able to go back as essential workers if they've got sort of time pressure, but it's still not very optimum. I mean, it's quite difficult, I think. For them, and it's hard to deal with actually.
So hopefully hopefully once things are back to normal, everyone kind of gets back into the swing of things and returns to their normal happy selves, and
we look forward to it.
Yes. Oops.
How's it going, Mav?
Okay, how you going?
All right, not too bad.
Hi, Mav.
Hey, how are you?
Good. How are you?
Good. Are you locked in home, or you're allowed to go free? Go free.
No, locked at home. Yeah. But for us Victorians, it's pretty. We're used to it. So,
Well, we've been locked up for a while, but I've managed to sneak in because we have some work that I have on contract, which is lucky because that makes us essential.
Oh, right. Yeah.
Cool. Yeah. So when are you moving? When are you moving up to the humid part of the country?
Yeah, after JCU in January. So so it's exciting. I'm looking forward to that. Well, hopefully they don't get COVID up there, because gosh, imagine that going from Victoria to
no kidding. Well, I guess when it's going to be that hot up there, it'll just kill it.
Yeah.
Probably. I mean, nothing else can survive up there.
So it's a bit unfortunate. We were supposed to be up there tromping around Mary Kay last month, but of course we can't go there. And I guess I can't go until April. Yeah,
absolutely. Yeah, it's just gonna be too hot.
Weren't you supposed to be up there, and did you go in July?
No, we planned that trip a few times, 4 or 5 times, and we haven't made it yet. But now I'm moving there, so that's gonna get that nicely. So hopefully, we'll probably be going around the same time. So we should see if we can
that'd be good. That'd be good.
Yeah.
All right. Cheers. I'm gonna hide myself now.
Okay.
It's hard to know what constitutes a quorum, but I'm guessing that the bulk of the people who are going to show up are showing up now. So Greg, whenever you feel like getting started, the rest of us will mute and...
Yep. Thanks very much, Louis. Okay, so I'd like to begin today by acknowledging the Ngunnawal people, who are the traditional custodians of the land upon which most of us are meeting today in the ACT and surrounding areas. And I'd like to pay my respects to their elders past and present. And I extend that respect to any Aboriginal or Torres Strait Islander people who have tuned in here today. And I'd also like to pay similar respects to the elders of the Wiradjuri people, and they are the traditional owners of the land where our speaker Melanie is sitting at the moment. And so now I'd like to welcome very much Dr. Melanie Finch to our Thursday afternoon seminar. Melanie's a structural metamorphic geologist at Monash School of Earth, Atmosphere and Environment at Monash University in Melbourne. She's the victim of obviously a very extended series of lockdowns, but seems to be bearing up very well. Melanie completed a PhD at Monash in 2016. She had a Humboldt fellowship in Tübingen in southern part of Germany after that, and then she came back to Monash in 2019 to her current position. Her research focuses on the links between deformation and metasomatism in shear zones, particularly subduction channels, as well as shear zones related to critical mineral deposits, which is something that is of great interest to us here. Melanie's also the recently appointed president of WMESA, which is the Women in Earth and Environmental Science Australasia. So that's an organisation to support and network female scientists in those disciplines. And in 2021-22, she was nominated as a superstar of STEM, which is fantastic. So it's really good to have you here, Melanie. Thanks very much for accepting our invitation. And today you're going to tell us about enigmatic structures in ductile shear zones. So over to you.
Thank you so much, Greg. Thanks for that introduction. Yes, so enigmatic structures in ductile shear zones. What do I mean by enigmatic, you might be asking? So I'm just sort of talking about, structures that we see in shear zones that are a bit mysterious, that we don't really understand yet. So when I look at this picture, when we all look at this picture, you probably see a lot of things that you recognise. There's microfiche, SC fabric, you might be able to see some recrystallization here, brittle fracture up here. So we understand why those sorts of microstructures form, but there are a few remaining that we still don't quite understand, and those are what I've been focusing on in my research lately. So just to get us all on the same page, let's look at what a ductile shear zone looks like. So this is a granodiorite from Cap de Creus in northern Spain, which is a beautiful spot right on the Mediterranean, and really great for structural geologists as well. So you can see here we have a leucocratic dike that cuts through and has been offset by a number of ductile shear zones here and up here as well. And you can see what these shear zones have done. They've offset this dike off to the left. And then down here as well, this part of the dike has been offset to the left relative to the continuation, which would be over here somewhere. So this is what ductile shear zones do. They move rocks around. They're like rock conveyor belts. So if we have a zoom in the area down here, you can see what they look like close up. So this is the shear zone in through here, and you can see that the minerals are really deformed and stretched out. You might be able to identify some SC fabric, and I'll explain what that is in a moment. And we've got some lozenge-shaped grains, and so the rock has gone from what was up here, like more equant sort of grains, more of an igneous sort of texture, to this sort of thing down here. So we do understand some of the processes that occur down here and why this through here looks the way it does. And we can have a look at how that process starts by, if we have a look at this circle, that at the beginning of dextral shearing, then the situation is like this. So we have instantaneous stretching axis, one in this direction, so we get the most stretching along here, and then this is the most shortening along here. So what that means is that as soon as a rock begins shearing, then we get the formation of S-planes, so parallel to this axis here and perpendicular to this axis there. And then all the lines in this orientation, in almost all these orientations, will rotate during simple shear, or shearing involves a component of simple shear. And in this orientation, clockwise. And so what we see is these S-planes rotate towards the shear zone boundary, and then eventually they end up parallel to the shear zone boundary, and then we call them C-planes. So together we call this SC fabric, and these C-planes, they don't rotate. They're like, well, they are not supposed to rotate. They're lines of no rotation along this line here, and so they kind of stay more or less stable, and then we get new S-planes forming in other areas. So this is one example of a structure that we understand well, and there are many other structures that form in ductile shear zones. So, we have SC fabric there and lots of other things as well. And we'll be seeing some of these today a bit later on. And a lot of these we understand really well. Ductile shear zones form in the region, in the crust. They form in the region of the crust that can deform plastically. So, schematically, we're talking under the brittle plastic transition, and that's where rocks are hot enough so that the crystals can deform in a ductile way. Up here, deformation is accommodated by faults and by brittle fractures. So we're looking at structures that form down here. This is really schematic in nature. This depth as well changes a lot, but that's just to give you a sense of the sorts of areas these things can form in. So why do we care so much about ductile shear zones? Well, they are really important for understanding how stress and strain are accommodated globally. So ductile shear zones accommodate movement on all the different plate tectonic boundaries. They're really important in lots of different places, and they get studied a lot in places like the Himalayas, where they're really important for understanding the shear zones. It's really important for understanding how the mountains formed and the tectonic history of the region. So by understanding the way the structures form, we can understand how strains are accommodated in those sorts of regions. So the Himalayas is one of the places that I've worked and looked at the shear zones there. And in that region, so this is a block diagram of the Himalayas, there's the Indian plate and there's the Eurasian plate, and between it we have the Himalayan mountain range. And you can see here labelled a number of shear zones. So we've got the main boundary thrust, the main central thrust, and the South Tibetan detachment system. And these three major shear zones accommodated quite a bit of the strain that thickened the crust and caused sort of the uplift of the Himalayan range. They're really important structures. You'll note that two of these are thrust sense, this one, and one is normal sense. So a normal sense shear zone in the type example of convergent tectonics is pretty exciting. And that's the region that I've focused a bit of my work on. And if you want to know more about why that's there, then you can, there's lots of papers on that, you can look those up. So yeah, it's a really exciting place to work. Now, the amazing thing about these shear zones is their lateral continuity. So if we have a look at a map of the Himalaya, then we've got those major shear zones marked in. So the STDS, South Tibetan Detachment System, in there, and then the two thrusts, the main central thrust, the main boundary thrust. And you can see that they extend along the entire length of the Himalaya. So from here all the way across to there. And so this is about 2,500 kilometres, about the same as the distance from Melbourne to Townsville. So it's huge, right? These mountain chains are huge, and these shear zones are incredible. So we work up here in a region known as Zanskar. And so focusing in up here. And what we had a look at here is this South Tibetan detachment system in a region where it's known as the Zanskar shear zone. So that's the same thing. So we wanted to have a look at how the Zanskar shear zone, why the Zanskar shear zone formed, and how it related to earlier periods of thrust shearing. So it had been previously reported that this Zanskar shear zone overprints an earlier stage of thrusting. So we looked at these different structural domains, and here in this domain 2A, we saw rocks that really, represented the normal shearing of the Zanskar shear zone. So they look like this, beautiful orthogneiss with SC, C prime fabric. And when we took a sample of this and had a look at a thin section, this is what that thin section looked like. So that's from the first slide. And you can see it's quite nice the way that the different layers have accommodated strain differently. So we've got, that SCC prime fabric down here, microfiche with the muscovite, whereas up here there's a feldspar class that has undergone brittle fracture, and those pieces have recrystallized in between those fractured pieces. So and the feldspar is a lot stronger than the micas, and that's why there's that difference in the response to deformation. A lot of familiar structures in there, and a lot of stuff that is really easy to understand, which leads us to a place which is much harder to understand. So then we had a look at the rocks in here in domain 3, and this is where the normal shearing of the Zanskar shear zone overprints an earlier stage of thrust shearing. So this is a view, so I'm standing on one side of the river and taking a photo of the other side of the river, and you can kind of make out that we've got SC fabric that just defines thrusting on this side, and then those planes are dragged into this normal shear zone there. So we've got this thrust shearing overprinted by normal shearing, and we see that at all scales. So also see that in outcrops. It's a little bit difficult to see here, so I outline the structures there. And so we've got thrust shearing, again overprinted by normal shearing, lots of folds in here, which didn't really understand what they had to do with it at the time, but that becomes relevant later. I know they're really hard to see, but it's just to give you a sense, and I'll show you a thin section in a moment. So overprinting shear sense like this, where we're shearing in one direction, overprint shearing in the opposite direction, is relatively common around the world. So this is another example from the literature where there was top to the east shearing, and you can get that from the asymmetry on this bit of the dike there, the way that's been sheared into a sort of sigma shape. And then overprinted by top to the west shearing, and you can get that from this asymmetry here, which is, it looks like it's sheared the other way. And there's another example in thin section. So this is overall shearing, the dextral, relative to what we're looking at here. But there are areas, there are structures in here that indicate sinistral shearing. So conflicting shear senses in some of these samples. So they're relatively common, these instances of overprinting shear sense. So on this map, you can see them indicated. Ignore the green squares, but if you look at the stars and the blue dots, that's instances where shearing in one direction has been overprinted by shearing in another direction. And in a lot of these cases, the shear planes are coplanar. So the later period of shearing has used the same shear planes as the earlier period of shearing, but it's just that the direction of shearing has switched. And that makes sense because shear zones are weak. So if you're going to shear a rock again, it's easiest to do that in a place where the rocks are already weak. Really common, and more common in places that have been really well studied, like the Alps and the Himalayas. But also, Mount Isa, we see this as well. And I think, probably this sort of thing is underreported because, as I'm going to show you, it can be a little bit hard to understand what these structures are telling you. So I'm particularly interested in opposite shear senses when there's been multiple stages of deformation and when the shearing is coplanar but with an opposite shear sense. So what I mean by that is we get shearing in one direction, which can form something like this, SC fabric in this direction, and I want to know what happens when you shear it back the other way. So I expect that you form hybrid microstructures. You wouldn't just go straight from something like this to something that's kind of like the reverse. So what do those hybrid microstructures look like? And, I think that from working in places where we see these sorts of things, I think in a lot of cases, these are outcrops that we go, I don't really understand this. I'm just going to keep walking. So I think that this work that I've been doing on these opposite shear sense, shear zones is about trying to generate an understanding of the structures we expect to see so that we can recognise them more easily in the field. So back to this example here. Now we took a sample of this and had a look at it in thin section, and that's when life got hard. So this is what the thin section looks like. This is a scan. So this is about 2 centimeters on this side. And it's a mess, right? Like, it's hard to see. What can you see here? Right? It looks really, these structures look weird. So in some places you can identify things that you recognize and can attribute to a particular shear sense one way or the other. So we have, you know, some SC fabric down here that indicates shearing in that direction, and some up here that indicates shearing in the other direction. So that's okay, because we know that this rock has been sheared in 2 different directions. We're trying to look for structures like this. But then there are lots of strange things. There are disharmonic folds. There are these layers of biotite that kind of just stop, and they seem to sort of cut off these folded layers. And there are folds that like are folded and then stop being folded, you know, in through there like that. So that's pretty weird. There are these hook folds down here that just sort of terminate, you know, who knows why. And then there are these clumps, these big clumps of biotite in through here that have kind of odd shapes as well. So I worked on these rocks when I was in my 4th year of undergrad when I was doing honours, and I had no idea really what I was looking at. And so we didn't use many of the structures in here in the paper that we wrote. But I've wondered ever since what these structures were about, why they formed, how they formed. So 11 years later, I decided that it was time to revisit these rocks and finally figure out what those structures are and what they're trying to tell us. So this process started about 5 years ago when I did a postdoc in Tübingen. And I went to Tübingen to do a postdoc because I really wanted to learn how to use this numerical modelling platform, L. So there's a group in Tübingen who are specialists in this, Paul Bonds and his team. And so there I got to figure out how to get this thing working. And the reason I wanted to do that was because of that problem I just described, but there were other structures as well that I had wondered about. So things I'd seen in the field, and I'd said to, you know, my supervisors, or I looked up in papers like about how do these form? Like, what do we know about this? I don't understand how this would form, you know, from what we know about how, you know, rocks accommodate strain. And you know, it became clear to me that there are some things that we just don't know yet. So I wanted to figure those things out, and that's why I went to do this postdoc. So what is L? L is a microstructural modelling program. So we've got, you digitize a microstructure, looks like this. We define these grains, or we call them flins. And what these are just, you know, boundary nodes, B nodes, that are connected together by straight lines. And then in the background behind this, we have U nodes, or unconnected nodes. And these are cool because these store information about strain rate and stress. So that's really useful information to have to understand what's happening in the models. So the way that this works during simple shear is that we have this starting microstructure. You deform it 1 step. And in the models I'm using, 1 step is a gamma, a shear strain of 0.02. And so 1 step, and the model kind of leaves the bounding box, and then we wrap it back around here and reposition it so that we can just keep shearing the microstructure to really high strain. So it uses full field viscoplastic deformation code. So you can read some L papers to figure out if you want to know more about that. And yeah, and so the deformation is accommodated by dislocation glide on crystallographic slip systems. So if we have a look at this thin section here, the way that these minerals are deforming is by, you know, is according to the strength of their slip systems. So micas have a really weak basal plane, so they deform very easily along that basal plane once that, you know, basal plane is oriented correctly with respect to the strain. So we're able to simulate those crystallographic slip systems in L. We can give each slip system a different strength or a different critical resolve shear stress. And so we're able to sort of simulate the strength difference between these minerals and between slip systems. So that's pretty cool. So in the models I'm showing you today, I use a microstructure that's like this, and it's got 3 phases. And the weak phase is supposed to sort of represent mica. It's in black here, and so that has a weak basal plane, and yeah, and it's weaker than the other two phases. Then in white, we've got an intermediate strength phase, and that's supposed to be like quartz here. Has the same slip systems as quartz, the same sort of crystallographic model as quartz. Yep. And then we've got feldspar, which is the strong phase, like you can see here. We simulate, simple shear in steps of gamma change of 0.02. So that gradually builds up the finite strain over time. So for instance, over 18 steps, we get to a gamma, a finite strain of 0.36. But in the models I'm showing you today, we go much, higher than this. So yeah, I wanted to see what happens if we've got a microstructure like this and we shear it under dextral shear for, just say, well, in this example, I'm going to show you is for 300 steps. And then we shear it back the other way for 500 steps. So I want to see the microstructures that form. So let's have a look. Now, what you see is the first thing that happens is that, we get alignment, that S-plane orientation. So, parallel to the instantaneous stretching axis. And then the weak phase rotates over into parallelism with the C-plane, just like we saw in that schematic example right up at the top. So forming a nice SC fabric here, and I wanted to do it this way because I thought, we want to develop sort of the microstructure in one direction and then shear it back the other way. So we kind of get a realistic microstructure for the period of sinistral shear to overprint. So now we're going back the other way. So sinistral shearing, and we're going to see what happens to the microstructures. So you might be able to see that these S-planes, they're becoming more vertical. It's a little bit hard to see, but they're rotating anti-clockwise, and they enter the maximum shortening direction, and so they fold. So we get folds in through here. You can probably pick those out. Takes a bit of getting used to. So we've got folds that have an axial plane parallel to the stretching axis, and then they rotate anti-clockwise. And as they do that, the amplitude increases and the folds become tighter as well. What we start to see is that with increasing strain, we get something like this. So the folded layers are completely transposed into like an S direction for the sinistral shearing and starting to form that SC fabric for sinistral shear. So yeah, really tight to isoclinal folds through here. You can still pick some of them out, and that's the end. So otherwise known as when the model crashed. So that's how they form. So now I'm going to go through that step by step. So by step 300, this is where we're still under dextral shear. So this is this microstructure that we ended up with at step 300, and then started shearing back the other way under sinistral shear. So this plane here, remember, so we've just got this basic SC fabric here. This plane here is this yellow plane there, and you can see that it's rotated anti-clockwise, under this sinistral shear. So that has entered this shortening field here under sinistral shear, which means that it has been an orientation where it needs to fold, where it folds, and so we develop all these folds through here. On average, the sort of axial plane of those folds is something like this, relatively, pretty much parallel to this sort of orientation here. So that's all, that all makes sense. So that's by step 530, and gamma of around 10. The next thing that happens is, so that's an outline of the folds, so you can see them a bit easier. And then the next thing that happens is these folds rotate anti-clockwise. And so the axial planes are more sort of parallel to the shear zone boundary on average. And so you can see an outline of the folds through there. So some of them are close to parallel, some are still at an angle. And the amplitude has increased and the folds have tightened as well. So the next thing that happens is that we get these really weird looking structures where we've got these hook folds through there. So it's really sheared out folds. And we're starting to sort of get those aligned to the S and C planes. So they've been rotated in further amplitude increase, like this. So I'll take those away so you can see it. And then the final stage at step 800 is that we've developed an SC fabric that, you know, kind of convincingly looks like it belongs under sinistral shearing. So I'd say that's kind of complete transposition of the microstructure. So that's really cool. I finally have this answer about what I was seeing there, because these sorts of structures, these sorts of weird shapes of these micaceous phases, this truncation of the folds, that's kind of around sort of this sort of step within the model. So we have, you know, these folds that truncate at layers of weak phase that are parallel to the C plane. So all of that is starting to make sense. So this is a work in progress, something that I'm working on now. I'd love to get your feedback on it and hear about what you think. So the next steps in this paper that I'm working on is to look at the effect of pre-existing microstructure. So I showed you an example where there were 300 steps of dextral shear and then sheared the opposite way, but I've done models where there's 100 steps of dextral shear, so start shearing under sinistral shear at this point, or at this point, or at this point, or at that point, and to have a look at what the effect of the pre-existing microstructure is on the microstructure that then develops under the opposite shearing, opposite shear sense. And the cool thing about L is it's really easy to quantify the microstructural change. So for instance, I can have a look at the aspect ratio. So, you know, when we start off, things are pretty close to an aspect ratio of 1, so pretty circular grains. And then under normal, sort of, this is just under sinistral shearing with no opposite shear sense. So under normal sinistral shearing, what we see is that the grains become more and more elongate. So you get an increase and then you kind of get a decrease, a small decrease in the aspect ratio. The story is quite different, as you can imagine, in these hybrid microstructures. So if we have a look at a model where there's 200 steps of dextral shearing and then we shear back the other way, then what we see is that there's a decrease in the aspect ratio. So the grains become, so we go from something that looks like this to something that looks like that. And you can see that the grains have become more equant, and that's what's reflected here. And then they stretch back out again in the opposite direction. But it's not the same for every model. So if there's 500 steps of dextral shearing at the start, then the microstructural evolution is quite different. So we get a small increase in the aspect ratio, and then a decrease and then an increase again. So we're looking at the causes of those different evolutions, because I think that's quite interesting. And there seems to sort of be an evolution here, a pattern here. This is a mess, but you know what you can see is we've got this pattern of a certain pattern here that's repeated for some models, but not reflected in other models. These are all different start steps. So it seems like the start step is pretty important. Whether or not, so I also need to compare this to naturally deformed rocks. So do naturally deformed rocks actually do this, or is this a modelling thing? I think there's evidence that naturally deformed rocks do this, but that's something I'm investigating as well. Another thing we can look at is strain localization. So that's F, the degree of localization. It's really easy to calculate with L. So in a normal model where it's undergoing sinistral shearing, then what we see is that the localization increases with, over the model steps, so with increasing finite strain. There's a bit of variability, within the model, but it kind of levels out at this sort of point here. Whereas if there's a period of dextral shearing and then sinistral shearing, then things are a bit more complicated. So if there's 100 steps of dextral shearing, then there's a decrease in the localization factor and then an increase. And that makes sense to me, because it's like, well, your structures are all rotated around the wrong way. So it's going to be hard for those to accommodate shearing in the opposite direction. So you've got to rotate them before you can accomplish like effective strain localization. So, that makes sense. But this doesn't make that much sense to me. So if you have 600 steps of dextral shearing first and then shear it back the other way, then the strain localization is higher than if you just sheared it in one direction. I have some ideas on why this is the case, but it's cool to see that, there's an effect of this starting microstructure. So yeah, that's a work in progress. So now I am going to switch topics slightly and look at another enigmatic structure. And so this is a C prime shear band. So we've got, C planes in this orientation parallel to the shear zone boundary. We've got S planes in this orientation, which, inclined in the opposite direction to the sense of shear. And then C prime shear band. So these dip 15 to 35 degrees from the shear zone boundary in the direction of shear. They've also been called in the literature extensional crenulation cleavage. So if you've heard of them, then I'm talking about the same thing. Yeah. So yeah, we understand this really well, as I've described. C prime shear bands have proven to be a bit more enigmatic. And this is not for lack of research. So a lot of people have looked at C prime shear bands in naturally deformed rocks. And since about 1980, these have been investigated. And there's been a few different theories as to why they form. So it's been suggested that they nucleate on the plane of maximum shear strain rate, or they could represent flow parallel to the shortening eigenvector, or they could form during the last stage of shear zone activity. And this one, is thought because they often cross-cut other structures, so it makes sense from that point of view. There've also been experimental studies on C prime shear bands. These have looked at deformation experiments on three-phase rocks, so quartz, feldspar, and biotite. And they've manipulated the strength contrast between the different minerals by changing the strain rate and the temperature and the pressure as well. And then they can simulate different strength contrasts, so 10 times, 25 times, and 45 times. That's the strength difference between the weak phase and the strong phase. And they find that when there's a low phase strength contrast, that will more likely to form an SC fabric, but when there's a high phase strength contrast, then that's when C prime shear bands form. So other work has also found that the strength ratio between the minerals needs to be at least 3 to 5 times, and that you need at least 20% weak phase for these C prime shear bands to form. So what that means in these rocks is 20% biotite. So that gives us 2 variables that are very easy to manipulate in L. So that was a great setup for an experiment. So that's what I did. I looked at different proportions of weak phase and different phase strength contrast and made 12 different models so that I could look at the effect of these 2 variables. So we had the weak phase, had a weak basal plane to simulate like a mica, so the weak phase was 10 times weaker than the other, the basal plane was 10 times weaker than the other planes in the weak phase. And then the intermediate phase was either 1.5 times stronger, 2.5 times, or 4 times stronger than the weak phase, and then the strong phase was double that. So yeah, we can have a look at the effects of these different conditions. I'll show you a few examples. So here I've got 5% weak phase. You see something black grains here. The strong phase is grey, the intermediate strength phase is white. Over here we have strain rate. It's very cool to be able to watch the strain rate while the microstructure is developing. We also get the stress, but it's only so much you can fit onto one screen. So I'll talk a little bit about what stress is doing while we have a look at this. So the first thing you can see is like what we saw in the previous models. So those alignment to the S plane there, and then the weak phase rotates into parallelism with the C plane. In places where the weak phase has rotated in parallelism with the C plane, you see that it's at a higher strain rate. So that's where the strain rate localizes. So those are red over here. So at the top here, there's a number of layers of weak phase, and they're all parallel to the C plane, so they're all localizing a high strain rate. And that means that stress will be really high at the tips of those layers of weak phase that are at a high strain rate. You can kind of think of it like they're pushing on the strong phase and intermediate strength phase at their tips, and that pushes those intervening grains out of the way and allows these layers of weak phase to link up. So that's how that is accomplished, and that's something that experimental studies have found as well. So up here, we've got a C prime shear band that has formed. You can see it forms in a layer at a low strain rate that's adjacent to higher strain rate layers over here. And then it gets a funny sort of shape, and that's because it's folding. So that has sort of entered the shortening direction, and it's folded and kind of collapsed, and the layers around it have folded as well. So this is one way that asymmetric folds form in these models under simple shear, and those folds often will then rotate into sort of parallelism with the shear direction as well. Up here, there's a layer of weak phase that's trying to link up and form a kind of through-going plane of weak phase, but there's not quite enough of it up there for that to happen. So you'll see that happen in some other models. So we'll move along now to a model with 15% weak phase. So here we've got a medium phase strength contrast, and yeah, obviously more weak phase. So grains quickly rotate into parallelism with the C plane and form that nice SC fabric. Here we've got a lot of more equant grains in grey of the strong phase, and they, even though there's sort of a medium phase strength contrast, so it's not a high phase strength contrast, they retain their equant shape, some of these grains, to quite high strains, because and that's because the weak phase is accommodating a lot of the strain rate, a lot of the strain within the model. So C prime shear bands form in this as well. And what you'll notice, if you've managed to catch one of these things forming, is that they form from layers that are parallel of weak phase that are parallel to the shear zone boundary that rotate forwards. So they rotate forwards, and then they either shorten and fold, like the one down here and the one here did, or they simply rotate backwards and become C planes again. So yeah, so we've got this forward rotation and back rotation. So they're quite ephemeral features as well. So that's an interesting feature. Here we've got a layer of weak phase that has managed to link up. So that will partition the strain rate for the rest of this model. So this becomes quite boring to watch. So we'll move on to the next model, which is 30% weak phase. So you can see, yeah, we've got more weak phase in this model. And what you can see early on is we have these vertically oriented structures that have now disappeared. But those are C triple prime shear bands. So not C double prime shear bands, sorry. So these are like at a high angle, and they show antithetic shearing. So shearing in the opposite direction to the overall shear sets. And that's because they're accommodating rotation of sort of lithons of strong phase. I'll show you again in the next model where it's a bit clearer. So quite a nice SC fabric that's formed through there. So these grains, this is a low phase strength contrast. So the grains here are more similar in strength than what we saw in the previous model, but even so, the strong phase remains relatively equant to, in some cases, because the strain is accommodated by the weak phase. So we've got a C prime shear band in through here, and it looks like that one has, it's rotated forwards and it's shortening, and then the layers around it will fold. You can see that there. So in other areas, the C prime shear bands rotate forwards and then rotate backwards again. So when there's a higher proportion of weak phase, the strain rate is more distributed throughout the model. That makes sense. There's more places for it to sort of localise in the weak layers. And what we sort of see, the locus of maximum shear strain rate kind of jumps around from layer to layer. So it is highest sort of down here at the moment, but then when shearing gets a bit hard here, then it might jump up here. Yeah, so sort of jumping around a bit. Okay, so we'll move on to the 45% weak phase model. So here are those vertical C double prime shear bands. Down here you can see a rotating lithon of strong and intermediate strength phase there, and that's causing the formation of these vertical sort of shear bands in through there. And this is similar to my colleague Hal Ran. He has a paper that looks at L and the formation of C double prime shear bands, and found a similar sort of thing that they can form between these sort of grains or clumps of grains of the strong phase or the stronger phases. So in these models that have 45% weak phase, there is obviously there's a lot more weak phase, so we get some more of an anastomosing shear zone through there, and a lot of the strain sort of localized to lots of different places in there. We still get C prime shear bands, so just that normal forward rotated shear bands, but they do seem to rotate backwards quicker, or they fold quicker, so they're a bit more ephemeral in these models. So if you want to take a closer look at these videos, they're all available on my YouTube channel, so you can check them out there if you want to have a closer look. And of course, I'm happy for people to use those in teaching. They're good for teaching, so yeah, please feel free. Okay, so what do we learn about C prime shear bands? Well, there are two main processes that form C prime shear bands. So I didn't go into this too much when we were going through the models because it's a little bit difficult to see. So I've just got some still images to show you what the two processes are. So the first one is when there's this, high stress in a hard phase bridge. And what this does is, so if we have a look, we've got this layer of weak phase, it's almost connected up. It's just got these hard phase bridges in between. And that means that those areas there, so this is stress here, I'll finally get to see some stress. So there's stress in there. And what you can see is that high stress, it causes, and the high strain rate in the intervening layers causes folding. So there's a folding through here, you can see it here. So it causes shortening in parts of the model. And so that, in this case, this C prime shear band, rotates forwards just to accommodate as a mechanical response to that shortening in that part of the model there. So it's got nothing to do with what's happening in this, layer of weak phase itself. It's more to do with what's happening elsewhere in the model. And this is like a mechanical response to that. Then the fate of this particular C prime shear band is that once the strain rate has sort of decreased down here, then that C prime shear band rotates backwards into parallelism with the C plane. So it's ephemeral. The second process that forms C prime shear bands is a strain rate increase in part of a layer of weak phase. So here we've got kind of a semi-continuous layer of weak phase there, and it's at high strain rate here, but at lower strain rate there and there. And so in response to that, this part here needs to rotate forwards to sort of accommodate that high strain rate there and there as well. So it rotates forwards to form a C prime shear band. And then once the strain rate is alleviated here and here, or reduces, then it rotates backwards again. So, yep. That's what happens there. So we found that C prime shear bands, they don't form when there's 5% weak phase and a low phase strength contrast, but they form in all other 11 models. They're more common when there's more of them when there's a high phase strength contrast, but they're more ephemeral in 45% weak phase models when there's more weak phase. So this is just saying C prime shear bands rotate backwards and become C planes, or through the process we were just looking at, but they can also shorten and fold. So this is that in slow motion or stop motion. So we've got a C prime shear band there, and it it kind of rotates too far, enters the shortening field and folds, and then it can also form these sorts of X shapes as well. And we see these in natural settings as well, these X shapes. So this is not a high-res photo, but there's similar sorts of structures reported in these naturally deformed rocks as well. So they could be forming through similar sorts of processes. So back to what I was saying sort of at the start of this part of the presentation. So previous research has suggested that C prime shear bands form for a range of reasons, and that you need at least a strength ratio of 3 to 5 times and at least 20% weak phase. But our results don't really tally with that. And that's, in part because we're 100% simple shear in these models, which is not what these things are deformed at probably. So that explains part of the discrepancy. So our models instead suggest that C-prime shear bands do not nucleate on the plane of maximum shear strain rate. They don't require general shear, which is under pure simple shear. They don't form at the last stage of shear zone activity necessarily, but they do, cross-cut other or offset other structures. So I can understand where that's coming from. And we only need 5% of weak phase, a bitype, for them to form if there's a moderate phase strength contrast. So at particular conditions, we can expect to see them even when there's only a small amount of weak phase. If you want to read more about that particular work on C-prime shear bands, we published a paper on this last year. So it's available in the Journal of Structural Geology, or you can email me for a copy, and all the movies are available on YouTube. So that brings me to an end of these enigmatic shear structures. I'd be happy to take any questions.
Hi. Hi, Melanie.
Hi.
Very cool modeling work. I'm curious about how to determine the stress-strain relation in your model. Is this based on experimental data or other models?
So how did I determine the strength between the different phases that I inputted? Is that what you mean?
Yes. Or I think you showed the strain rate in your model as well.
Oh, yeah.
So how do you, what kind of microphysical mechanism? You showed, I think, deformation on the slip system. So is your model based on that kind of microphysical mechanism?
Yeah, so the grains are deformed by dislocation glide on the crystallographic slip systems and the critical resolved shear stress, which I set. But the strain rate is recorded. We record the strain tensor, the full strain tensor, and then the strain rate is extracted from that. From the U nodes. So at each point in the model. I'm not sure if that answers your question.
Okay, yeah. I'll think of a better way to ask this question. Yeah, thank you. Yeah.
Do you have any other questions from anyone?
Yeah, I've got one.
Richard.
Yes, Tony, thank you. Extraordinarily instructive. But can I take you back from the micro to the macro? You said you'd been working up in Zanskar and Himalayas. And after this experimental modeling computing effort, what have you learned new about the thrusting in the Himalayas that you didn't know or other people didn't know before? Where has this opened up a new vista on the development of the Himalayas?
Yes, well, I hope that I do get to a place where I'm able to provide a very interesting answer to that question. At the moment, I'm thinking that, because this is a work in progress, I'm thinking that it might be interesting that the strain localization is different in shear zones that have had this pre-existing sort of this early history of shearing in one direction and then they've been sheared in the opposite direction. So that might mean that the shear zone has to widen when it's overprinting a prior shear zone. So that's sort of something that might end up being interesting, but I haven't explored that enough yet to know. But yeah, I'm not sure what the implications will be yet, but I hope that there are some.
Very good, thanks.
Thanks.
Yeah, another question?
Yeah. So when you look at the natural rocks, that's a 2D section in a 3D rock, right? And when and your modeling and stuff, that's done in 2D. So would there be any difference if you would model it in 3D and then take a section, or would it be all about the same?
Well, the models would crash a lot more, so that would be one difference. Yeah. So yeah, it is better to be able to see things in 3D and model in 3D. yeah, so yeah, it would be better. And there's a version of L that's being worked on now that we'll be able to model in 3D. But yeah, we're limited by the strain, the finite strain you can reach with those models at the moment. So I think, yeah, there's always a limitation when you're modeling 3D features in 2D. But I think, you know, especially in simple shear, in pure simple shear, which we can talk about how realistic that is, but in 100% simple shear, it hopefully doesn't make too much of a difference to the features that we'll actually see in the rock.
Okay, and a follow-up question. A lot of those phases, you know, you have quartz, then you have the garnets and micas. So those things are things that have quite a lot of density difference. And if you take something like that and look at that in X-ray CT system, will you see the textures in 3D and be able to take a natural rock and kind of look at one thing through different sections and compare it with the modeling? Is that something that can be done or has been done?
So sorry, I missed, I think the middle, which, have a look at which system, sorry, I missed the middle, I think.
An X-ray CT, so.
Oh, yeah.
Yeah.
Mm-hmm. Yeah, no, that's not something that's been done, but I think that would be interesting. I guess you would see sort of what we see in these models is a evolution over increasing finite strain, and different parts of a naturally deformed rocks would probably achieve different states at different times depending on the mineralogy in that local area. So different types of microstructure in different places. So yeah, that is a comparison that would be interesting but hasn't been done.
Melanie, this might be a naive question, but I mean, how far can this modelling approach extend in terms of pressure and temperature? So what I'm thinking is, could you investigate the origin of sheared mantle xenoliths, for example? So these are the deep mantle xenoliths from cratonic lithosphere, and quite often the deepest ones are really sheared or almost myelinitic, but with big lumps of garnet, sort of like boulders in the stream. And it's contentious as to whether that's some sort of fluid related to magnetism that brought them to the surface, or whether this is some sort of tectonic process. So can those models extend to those sorts of more extreme conditions? Yeah,
so well, that sounds really interesting, and I want to follow that up for sure. So the yeah, and the way we're just simulating temperature is by giving the minerals a particular critical resolve shear stress that would apply at a given temperature, so sort of simulating it in that way. So that would be easy to do. And I've been looking at, I've been sharing some eclogites with Al, and yeah, the problem that we have is that the matrix is so much weaker than the garnets, just say, that yeah, that things tend, the microstructure tends to get quite complicated around those garnets and the grains get really small and then it crashes. But yeah, I've been persevering and that seems to be working well. I don't think there's any reason why we couldn't investigate a question like that, and I think that sounds really interesting. Yeah.
Okay, I might get back to you on that one. Any other questions for Melanie?
Yeah, can you hear me, Greg?
I can hear you, Stephen.
Oh, okay. Hi, Melanie. That was a fascinating presentation, and to me it very much highlighted how when we look at rocks in nature, we're looking at post-mortem. And so things like L and the old in situ modelling we used to do with see-through analogues, which gave rise to L, really gives us lots of insights. The question I've got is, when you reverse the shear sense in that first part, went from dextral to sinistral, you started crenulating the structures in there. It looked to me like there might have been a bit of dissolution precipitation creep going on. Can you incorporate that within the L model currently, or are you stuck with constant volume?
We're stuck with constant volume at the moment, yeah, unfortunately. But yeah, they're just mechanical models. Yeah, but there have been people trying to get grain boundary migration kind of into L as well, and that would be a good day when that happens. And yeah, dissolution precipitation creep would also be amazing.
Yeah,
it'd
be great, because you're developing those mica quartz feldspar interfaces, and they tend to dissolve very rapidly in nature. So it'd be really neat to incorporate that at some later date.
Yeah, yeah. I'll have to talk to the crew in Tübingen, or figure out how to do it myself.
Yeah.
Yeah.
Anyway, thanks for a lovely presentation. Very insightful.
Thank you. Great.
Thanks.
Thanks, Steve. Any further comments or questions, discussion? All right. That looks like it. Well, thank you very much, Melanie. That was fantastic, really interesting. I'd love to try those videos on some of my second year students as a rank amateur teaching a little bit of structural geology. Sounds really like an interesting approach. So thanks a lot for agreeing to talk, and good luck with your future endeavours. And we'll see you later on.
Thanks so
Well
much.
done.
Thanks for the invitation. It was really